Hello students, welcome back. So in our previous part we discussed about the physical properties. So in this part we are going to discuss about the chemical properties. So what type of reactions does alkyl halides undergo? Do they react with metals? They undergo any kind of reduction or not? So all these concepts I will cover in this part. So let's start then. So in our previous video we have seen the physical properties of alkyl halides. Now we are going to discuss about the chemical properties of alkyl halides. So what are the chemical properties? What kind of reactions does this alkyl halides show? So let's get into more details. The haloalkenes are highly reactive class of aliphatic compounds. These are reactive because of the presence of polar bond, that is CX bond, where C is the electrophilic center where a nucleophile can come and can attack. So their reactivity is due to the presence of the polar carbon and halogen bond in the molecule. So in general, for a given alkyl group, the order of reactivity decreases as iodides are more reactive than bromides, which are more reactive than chlorides, which are in fact more reactive than fluorides. This is because of the bond instability of iodides. So if you see, iodide is relatively bigger than the other halogen atoms. So the CX bond length will be very high. The CI bond length is high. So if bond length is high, then bond dissociation energy will be less. So this I minus is a better leaving group. Okay. So because of the lesser dissociation energy or more bond length. So higher the bond dissociation energy, smaller is the reactivity. And if lesser is the bond dissociation energy, then higher will be the reactivity. So that's why halides are more reactive than chlorides and bromides. So let's see the chemical properties. The chemical properties shown by the alkyl halides. So the chemical reactions of haloalkenes are of 4 types. They are namely, one is the nucleophilic substitution reaction, second is dehydrohalogenations, and third one is reaction with various metals, and fourth one is reduction reactions. So here the first reaction is the nucleophilic substitution reaction. So it is basically a substitution where one atom or a group of atom is replaced by other atom or group of atoms. So such type of reactions are known as substitution reactions. So we know that in organic chemistry, so basically we have 3 different types of reactions. One is substitution, second is addition, third is elimination. So substitution, it may be electrophilic substitution or it may be nucleophilic substitution. So but the nucleophilic substitutions are very famous and they are important as well. So because a nucleophile will substitute the other atom. So that's why the reactions are known as nucleophilic substitution reactions. And we have the second class of reaction, that is dehydrohalogenation, that is the removal of HX, hydrohalogenations, that is HX. So if I remove HX molecule from a compound, then such reaction in which there is a loss of hydrogen halide is known as dehydrohalogenation reactions. And third is the reaction with metals. So metals like magnesium, sodium and lithium, they will react with the alkyl halides. So such reactions are the reaction with the metals, and fourth type of reactions are reduction reactions. So in this part I'll concentrate only on this nucleophilic substitution reaction, and in our next part we're going to discuss about the other 3 parts. So in this part I'll only discuss the nucleophilic substitution reactions. So what are the nucleophilic substitution reactions are? So in haloalkenes, the halogen atom is attached to the carbon atom, right? So since the halogen atom is more electronegative than carbon atom, so the bond between the carbon and halogen is polar in character, right? Because if you take carbon and halogen, due to the electronegativity difference between the carbon and halogen, so this bond is polar. This bond is going to have certain non-zero dipole moment, right? So this bond is polar bond, and if you take a bond between the similar atoms, then that would be non-polar because there is no any electronegativity difference So there is no any dipole moment. So those are non-polar, but here due to the non-zero electronegativity difference, so this bond is said to be a polar bond. Yeah, you discussed more about this polar and non-polar character in chemical bonding chapter. So due to the presence of the positive charge on the carbon atom, the nucleophiles can attack on electron deficient carbon, right? So if you see here, the carbon is electron deficient one, delta plus, and this is delta minus. So this is electron deficient. There is a lack of electrons on this carbon atom. So if some nucleophile which is searching for an electrophile, if that sees this carbon atom, then that nucleophile will come and it will attack this carbon atom, right? So because the nucleophile always attack the electrophilic center. Similarly, the electrophile will always go to the nucleophilic thing. So here the nucleophile will come and it will attack the carbon atom, and there is a loss of halide ion from here. So which I can represent pictorially in this image. So this is the halogen. So this is the nucleophile. The nucleophile will come and it will replace this halogen. So basically what the nucleophile is substituting the halogen atom. So that's why the reaction is nucleophilic substitution. So that is a substitution by a nucleophile. So the nucleophilic substitution reactions are of two types. One is SN1, another is SN2, right? So here the N implies nucleophilic, S implies substitution. So it is nucleophilic substitution. Then what does this 1 indicates? What does 1 indicates? So to know what is that importance of 1, we have to get into the mechanism, right? So in SN1 and SN2, the only difference is like both are nucleophilic substitutions, but one is, here it is 1, but here it is 2. So what is this 1 and 2? So let's know about it. So one kind of mechanism is SN1 mechanism. So where SN1 reaction is a unimolecular nucleophilic substitution reaction. So here the mechanism that comes from the kinetics, you have to know the kinetics of a reaction. So you might have known that if molecularity is 1, then that reaction is known as unimolecular. If molecularity is 2, then those are known as bimolecular reactions. So here it is a unimolecular reaction. That's why this one indicates the molecularity. 1 indicates the molecularity, is nothing to do with the order. It's not like that it is a first order reaction. SN2 means second order reaction. No, 1 and 2 are nowhere related to the order, but they are only related to the molecularity. So this mechanism is not a elementary reaction. In fact, it goes in 2 steps. So we know that the step which is slowest step is known as rate determining step, RDS. So in the rate determining step of this mechanism, there is only one molecule is involved, there is one species involved. So that's why it is unimolecular reaction. So you know about all these things once we get into the mechanism. So it is a 2-step reaction with a carbocation intermediate. So we know what is meant by intermediate, right? So if a reaction is a complex reaction which is occurring in 2 or more than 2 steps, then there are going to be intermediates form, right? So that intermediate, like it forms in 1 step, and that will be consumed in the next step. So it is like a temporary things that is formed during the reaction mechanism, right? So here it is a carbocation intermediate. It's very, very important. It is a carbocation is the intermediate form, and the rate is first order in alkyl halide and 0 in the nucleophile, and racemization occurs. So we'll discuss about this racemization in the coming slides. So if you see, there are 2 steps. So in the first step, there will be a formation of carbocation. So this is the alkyl halide we are taking, where these 3 alkyl groups. They may be methyl or ethyl or propyl, etc. And this X is halogen, which may be chlorine, fluorine or bromine or iodine. So here this bond is a polar bond. this bond is a polar bond, then this bond is going to be broken. So here we get a transition state, right? Transition state. So this transition state, there is a partial bonding in the transition state. So this is a full bond, but what happens here is due to the electronegativity difference, X will get a partial negative charge and C will get a partial positive charge. So during the transition state, this bond is going to be weakened. There is a partial bonding, and after that what happens is this transition state will end up here. So here we will get a carbocation. So there is completely, this bond is completely broken. So we will get this carbocation along with the halide ion. So this is the carbocation, right? Carbocation, that's a very important intermediate that is formed during this reaction. And so the reactivity of the different alkyl halides is mainly going to depend upon the stability of this carbocation. So if the carbocation is stable, then it will be easily formed, halogen is going to be lost easily, and if at all this carbocation is not so stable, then it does not form easily. So that's why those compounds which yield weak or unstable carbocations are not so reactive towards SN1 reaction. So this step is actually rate determining step, and during this rate determining step only one molecule is involved. So that's why it is a unimolecular reaction. So let's see what happens in the second step. So in the second step, this carbocation which is electron deficient, it will be attacked by the nucleophile. So nucleophile go and it will attack that, and there is a bond formation takes place. So the nucleophile attacks on the carbocation, forming the product. So generally the reaction ends here, but if the nucleophile is a neutral, then the third step will also takes place, that is the deprotonation step. So like if you take a neutral nucleophile, like if you take water, then this oxygen gives a lone pair of electrons, like it will go and it will attack, and the next step will be the deprotonation step, where the one of the H is getting removed, the proton will goes out, and you will get only the ROH as the product. So if it is charged one, if it is anion, then the third step is not required, but if it is a neutral nucleophile, then third step will also be there. So if you see the energy diagram, that what are the energy changes takes place during this mechanism. So this is the reactants, and will reach the transition state where this bond is partially broken, and after that this bond will be completely broken, and you will get a less energetic this intermediate. So this intermediate state we have carbocation and halide, and after that what happens is the nucleophile will go and it will attack this carbocation and will get the products. So this is the energy diagram. Forming the carbocation is an endothermic step. Here we need to break the bond, so we need to supply the energy, so that will be endothermic and slowest one. And second step is fast. The nucleophile will go and it will rapidly attack the carbocation. So step 2 is fast with low activation energy, and step 1 is slow with high activation energy. So if you see the rates of SN1 reactions, so as I told, the order of reactivity follows the stability of the carbocations. So the tertiary are more stable than secondary, which are in fact more stable than primary. So this is the order of reactivity towards the SN1 reaction, because the more stable carbocation will be easily formed and it will take less energy to form. And a better leaving group also increases the rate of reaction. So if I take one particular group, like if I take tertiary butyl chloride, bromide and iodide, so how I decide the rate of those molecules towards the SN1 reaction. So here in all the three cases you will get a tertiary butyl, you will get only this carbocation, right? So here, like which one is going to show more reactivity towards SN1, that depends upon the attached halogen. So if it is iodine, then it is a better leaving group, so this bond will be easily broken, so this carbocation will be easily formed, right? So a better leaving group will also increases the rate of reaction. And next is solvation effect. So the solvation effect is very important in SN1 reactions, because whatever the carbocation that is formed here, that will be solvated by the solvent molecules. So if you take what here, alcohol is the solvent, so the carbocation as well as the halide ion both are getting solvated, and this increases, this solvation will increase the stability of both of these ions, and energy is also going to be released. That energy is known as solvation energy, right? So always polar protic solvent favors the SN1 reaction by stabilizing the formed carbocation as well as the halide ion by the solvation effect. So if you see the structure of carbocation, it is planar, right? It is having an hybridization sp2. So yeah, this will be the vacant orbital, and this molecule is a planar molecule. So the nucleophile can go and can attack from the top, it can also attack from the bottom. So it has two ways, it has two paths. So if it goes and if it attacks from the top side, you will get this one, or if it attacks from the bottom side, you will get this one. So one will be the same one, other will be the inverted one. So if it is the same one, that is, if the nucleophile is there on the same side, at the same position of halogen, so we will get the retention, and if it is there exactly opposite, we will get inversion. So that's why the formation of the retention and inversion product is known as racemization, and is possible due to the planar structure of carbocation. Yeah, nucleophilic attack can occur from either side, producing the mixture of retention and inversion of the configuration if the carbon is a chiral carbon. So yeah, this is the stereochemistry. If it is S, then you will get S as well as R. So S means it is the same configuration of the reactant, but here it is inverted, right? So this is known as racemization. So that is possible due to the planar carbocation. So SN1 reaction produces a mixture of enantiomers, but usually there is more inversion than retention of the configuration. So you don't get both of these two in the equal proportions. You will get the inverted one in higher proportion, and the retention of the configuration will be in the less amount. Okay, so this is all about the SN1 reaction, right? So now let's discuss the second type of mechanism, that is the nucleophilic substitution bimolecular. The 2 indicates that it is a bimolecular. That means there are two molecules, two species involved in the rate determining step. So if you see here, this is the SN2 mechanism, where the nucleophile will go and it will directly attack the electron deficient carbon from the reverse side of this halogen. So here there is nothing like the formation of carbocation and all that. So the nucleophile will go and it will directly attack from the opposite side. This point you have to keep in mind. Always the nucleophile will go and will attack the carbon from the opposite side of the halogen. So here you will get a transition state where this bond is partially broken and this bond between the OH minus and C is partially formed. So yeah, this bond is partially, it's going to be formed and it's going to be broken. So this is the transition state. So soon after, what happens is this bond will be formed completely and this bond will be broken completely. So you will get this product, right? And this will be the leaving group. So it is a bimolecular because it is involving only one step and the two species are involved. So it is bimolecular. And yeah, if you see the new bond forming and old bond breaking at the same time. At the same time this happens. So one bond will be broken and simultaneously other bond is going to be formed. That you can observe in this transition state, and rate is first order in each reactant, and here there is an inversion of the configuration. You don't get any retention because here the nucleophile it has to go and attack the carbon from the reverse side of the halogen. So you will get you will get completely inverted configuration. You don't get any kind of retention, right? Because here there is nothing like the planarity, both sides of attack, all these things are not there. There is only one way, and that will finally yields in the inverted product. So this inversion is known as Walden inversion or umbrella inversion, right? So you can see here, initially the 3 hydrogens are like this. So due to the attack of this one, like the inverted umbrella, like if you take umbrella and if you put it like that, the air will come from the opposite side. What happens? It will be suddenly inverted. So the same thing also happens here. Yeah, this is the energy diagram where there is only one step. Before in SN1 there are 2 steps. Here there is only one step, simple transition state. This bond is going to form and this bond is going to break, and this is the product you are getting. So it is a one step reaction and the transition state is the highest in energy. So let us see the steric effects of the substrate on the SN2 reactions. So in SN2 reactions, in SN1 the stability of carbocation and solvation effect are important, but whereas in SN2 the steric effects of the substrate is very, very important, because if you see, like if I am taking these 3 molecules where you can see the pictures of these 3 molecules. So here this is CH3, H and H, but here there are 2 CH3s, here there are 3 methyl groups are there, right? So you can see this is the iodine. So on exactly the reverse side, this OH minus is going and it will attack, right? But in this case still it can attack, but it feels more steric because there are 2 CH3 groups. So CH3, this OH minus, the incoming OH minus will encounter the repulsion from these 2 methyl groups, right? Because of this is known as steric hindrance. So as a result, the OH minus it does not feel comfortable to go and attack the carbon because of this crowdiness, but here it will be even more crowded. So it does not have any space to go and to attack. So obviously this cannot undergo SN2 reaction, and this will show more possibility of undergoing SN2 reaction. So this is known as steric hindrance. So always the less bulky groups present on the carbon will favor the SN2 reaction, and if there are any kind of more bulky groups are there, then that will undergo the substitution through SN1 but not through SN2 because of the steric hindrance or steric effect. So this is all about the nucleophilic substitution reactions of alkyl halide, that is, one is through SN1 mechanism and other is through SN2 mechanism. So the remaining properties we will discuss in our next part. So students, in this particular part I discussed about the nucleophilic substitution reactions of alkyl halides. In that we discussed about the SN1 reactions and SN2 reaction mechanisms. We have seen the important aspects of SN1 as well as SN2, like the structure of carbocation, the Walden inversion, as well as the stereochemistry of both SN1 and SN2 reactions. So in our next part we will discuss about the other chemical properties. So keep watching for my next part.